I'm going to talk about the basics of finite element analysis. The physical phenomena, it can be any physical phenomena, is represented by a set of governing differential equations. These differential equations can be ordinary differential equations or partial differential equations. All physical phenomena in science can be represented by governing differential equations. If we don't know the governing differential equation, it means that the understanding is yet to be developed. So now we suppose we have to solve a problem in solid mechanics. Of a cantilever beam which is loaded at its free end, and I have to find a problem. I want to solve this problem by finding the displacement at each and every point. So my first step would be to develop the set of governing differential equations, and in case of solid mechanics, these governing differential equations are developed using equilibrium equations, which is Newton's second law. Strain displacement relations, and the constitutive equation. This constitutive equation is nothing but the stress strain relationship. Now we wish to solve the arrived governing differential equation, and the first way I can solve it is, the first thing I can do is to find exact solution. So for the exact solution, I will have to satisfy all boundary conditions and the governing differential equation at each point in the domain. Say this is my domain. So each point within this boundary is my domain. So mathematically, these points are in the domain. A and B are in the domain. Point C is at the boundary. Point D is outside the domain. So basically, I seek the solution of the problem within the domain and at the boundaries. So when I get the exact solution, the error is equal to 0 at all points within the domain as well as at the boundaries. The second way is to get an approximate solution. Why do we need an approximate solution? The answer is very simple, that it is not easy to get the exact solutions. We may have a very complicated domain, we may have a very complicated governing differential equation whose integration may be very difficult, and almost in most of the practical cases we will find that finding the exact solution is very difficult. Thus we go for the approximate solution. Again, the approximate solution can be arrived at we can get analytical solution, where we can have formulas say an infinite series. The second way is to get a numerical solution. The main difference is that in case of analytical solution we get the formulas where we can put the values and get the required value of the variable at different points of the domain. However, in case of numerical solutions we get the numerical value directly at different points. So this is not of current interest. We would be looking at numerical solutions, and one of the methods to get these numerical solutions is finite element method. As we saw in the exact method where our error was equal to 0 at all points within the domain and at the boundary, in case of finite element method, because it is very difficult to get error equal to 0 at all points, we follow a different strategy where we make these errors 0 in a weighted integral sense. So weighted integral of error is equal to 0. This error is nothing but left hand side minus right hand side. And omega here represents the domain. Thus, in finite element, the error may not be 0 at each and every point within the domain and the boundary. But when we integrate this error after weighting with a weight function, then the error should be equal to 0. Thus, in context of solving partial or ordinary differential equations, if we find it difficult to get a closed form solution, we use finite element approximations to get approximate numerical solution. Moving on to the steps involved in solving a differential equation using finite element method. So the first step is to discretize the domain into subdomains or elements. Discretize the domain into subdomains or elements. Taking an example of a one-dimensional domain, we can say that our domain is varying from x is equal to 0 to x is equal to L, and we can discretize it into number of elements. This is my first element, this is second, third, and so on up to n. The second step is to assume how the unknown variable is changing over the element. Over the element. Say we have a bar here and we are pulling it with a force of magnitude F. So our first step is to divide this bar into number of elements. And we wish to find the displacement at all internal points in the x direction. So I can assume that this displacement is constant over this element. Say the length of each element is HE, and this is our eth element. Okay, so here we have two nodes of this element. This is a one-dimensional element, and say this first node, it is numbered E, and the next node is numbered E plus 1, and assume that the length of this element is HE. Basically, we want the displacements at all internal points when we are pulling this bar. So I can assume that the displacement is constant over this element, or I can assume that the displacement U is varying linearly over this element. Or I can assume that it is varying quadratically over this element, so on and so forth. Thus, the displacement that we need to find, it may be a constant C, it may vary linearly with B and X as constants, it may vary quadratically as A plus BX plus C x square, where A, B and C are unknown constants. Now our next step is to to find the error in a weighted integral sense. That is, error into any weight function and integration of this term over the domain, and then we have to equate it to 0. Let's go back again to the bar problem. We are stretching this bar with force F. Here x is equal to 0, length of the bar is L, and we have divided it into elements. The governing differential equation for this bar would be now this is our governing differential equation. Thus error here would be this left hand side minus right hand side. We have to multiply it by a weight function and integrate it over the domain and equate it to 0 for each element. Thus we will have multiple equations for we will have the equations, then all number of equations would be equal to thus number of equations would be equal to number of variables per element multiplied by number of elements, and this is valid for a one-dimensional linear element. Into if number of nodes. So for linear element, say we have two variables at each node u and v, and we have two nodes 1 and 2. Thus total, and say we have 5 different elements, then total number of equations would be two variables per element and number of nodes, so into number of elements. Okay, I'm sorry, this should be node. Number of variables per node. Yeah. So our next step would be to assemble these element level equations and after assembling all these element level equations we will get assembly level equations. Then we can apply the boundary conditions. And the last step is to solve for the unknown. In the assembly level equations.